for joining me today for the talk, The Rotating Plasma Source as an Innovative Tool to Synthesize Fine Powder for Industrial Applications. This presentation will describe this innovative technology and how to take advantage of it to synthesize nanoparticles, particularly copper nanoparticles for industrial applications. We will go over some of the busy slides quickly and leave them as a reference, but then we will stop at some slides that have certain historical data or configuration. So the content is a science of the topic, the relevant technology, and a discussion about what we have presented. This is the first segment of the talk, talking about the science behind this innovation. This is one of the busy slides. So this is just a typical description of a nanoparticle synthesis processes. Some of these processes are chemical in nature or wet processes, and some others are dry processes, such as the physical processes, and they have different attributes and they vary in their qualities. Basically, the physical processes are top down and the chemical processes are bottom up, as this graph shows. The copper nanoparticles, they have special properties that are described in this slides, and they are can be used as a substitute for precious and noble metals such as gold and silver and platinum. I want to talk about the science behind the proposed concept, the thermionic emission phenomenon, which has been abandoned for a long time. Basically, this phenomenon is described by the Richardson equation and the Child-Langmuir equation. Child-Langmuir law. I want to show the Child-Langmuir law. Basically, I put the formula for the concentric cylindrical discharge, and we will talk about the implication of this later on in the talk. This is one of the ancient data from one of the Langmuir works, and basically it shows the evidence actually that the thermionic emission can grow actually higher if we can manipulate some of the discharge conditions. This is also some of the old data in the 60s and well-established data that shows even at 500 EV ions we can get a good sputter yield. This is a flipped cartoon that I get from one of the references, and it basically shows the this is the Langmuir sheath here, and this is basically the sputter etching process based on thermionic emission, and how we can use the sputter etch process actually to produce the particles. In this case, people were interested in actually sputter depositing a film here, but basically we can substitute the deposition substrate for a collector of the particles. This is another evidence actually that if you insert a probe close to the sheath of a bias plate, then the electric field will be distorted. Here it can be up to -12 extended. The technology behind this science is basically the so-called rotating plasma source. This has been developed in the labs of one of our affiliates, sister companies. It has been used to produce actual particles for many industrial applications, nanoparticles. And basically, in this configuration, basically it is a capacitively coupled RF rotating plasma source. And so we will show also. This is basically the video that shows the rotating capacitively coupled RF. Okay, so now the electrodes are on the outside. In our new configuration, we will be having a copper foils on the inside, and slight changes will happen. Again, I will reference the Child-Langmuir law for cylindrical configuration, as we can utilize that for another concept. For example, it's been well established for the fluorescent lamp. I like to bring this example because In this case here, people sort of worked out a large flow of current, and they had to use a choke or a ballast, basically, to limit that current, without which the discharge will just basically melt down. So this is an example where other factors such as the anode case and basically the anode conditions, actually, the anode conditions and what kind of cathode material we use and how we position them, we can get actually a lot of current that will strike the anode. In this particular example, this is a fixed discharge. This is not rotating, actually. This is fixed, this is another cartoon that I picked up from one of the references. So what I would like to point out here is that based on the Child-Langmuir law and from the original work of Langmuir, there's a proposal if there is a cathode that is in the form of a very thin wire, less than 1/10 of the thickness of the radius, actually, of the tube, then if it's strung horizontally and concentrically across the tube, and it can be used to emit basically electrons that will strike the anode if it is in the form of the tube inside. And so this is basically a configuration that we are proposing. This is a non-arc initiation process. Instead of relying on a spark or an arc to happen, this is basically a reliable way to string a solid along concentrically along the tube. And if we need rotation for manipulation, control, selectivity of the species, then we can introduce basically rotation as we showed before. Let's go on a discussion about the science and technology. I will just mention the word health physics issues, and then I will refer you to one of the references at the end of the talk, because whenever we deal with plasmas, with high voltage, with radiation, and also with nanoparticle synthesis, then we have to address these issues, and there will be a nice reference at the end of the talk about that. Thermionic emission technology has more physics to be worked out. Traditionally, it has been worked out from a chemical point of view, from chemical engineering point of view or chemical sciences point of view, but there is, it did not take much of the what it deserved in terms of attention. We need to model and map the electric field lines inside this kind of plasma discharges. This is very important. This should be assisted by qualitative arguments that will model this kind of measurements. Creative mathematical tools must be employed these days. Elements of chaos theory, such as logistic curves and maps and fractals and such, these things have room to be employed in such discharges and to reinterpret the data that people arrived at empirically before, and then we can advance this field of knowledge. Thermionic emission, this phenomena is as important, if not even more important, than photoelectric effect. So this has to be taken into account. Modern load lock powder handling systems are important if we need to control the oxidation of the oxidation degree of the nanoparticles we produce, particularly copper, so it doesn't get oxidized and we lose some of the very important parameters of what we produced. The concept fixed cylindrical discharge is based on a well-established fluorescent light technology. Configuration, aspect ratios, thickness of the walls, and such can be taken into consideration. The summary slide is another busy slide. You can refer to it later, which is basically summarizes what I've spoken about. I would like to talk about the references a little bit. The first reference is the biological responses to nanoscale particles. It's a very, very important reference. And the second one is about the collected works of Irving Langmuir. I urge you and encourage you to go back and look at these works. You can buy them on a Kindle from Amazon. Chapman, reference 3 is a good book. Also good reference book. And then I patented something, a concept also with the Saudi agency for patents here in Saudi Arabia that basically has a configuration for one of these discharges. Noah Hershkovitz spoke about sheaths in details, and this is in reference 5. And then there's a Chinese and Japanese group basically who motivated that work that I did. Basically, they discovered the properties of copper if it got associated with silica matrices, and the property for catalysis that it provides. And then 7 and 8 is references by our sister company Plasmatech in Turkey, and basically they done the rotating plasma source configuration and took data. And lastly, 9, there's a website that's basically talks about the fixed fluorescent lamp technology and its history and how it's been developed. So thank you very much, and I'm happy to take your questions.